On January 16, 1943, the ship called SS Skankstady sat quietly at the dock in Portland, Oregon. It was a new Liberty ship, only about 10 weeks old, freshly made at the Kaiser shipyards. There was no enemy around and no bad weather. The morning was calm and the water looked still. Then suddenly a loud cracking sound filled the harbor. In seconds, the whole ship split completely in half, the hull breaking from top to bottom like it was cut by a hidden knife. The sailors ran fast as the front and back of the ship bent in opposite ways, her body broken while still tied safely to the dock. The Schenectady was not the only one. That same cold winter, the ship called SS John P. Gaines also broke apart in quiet seas. Another ship named SSSO Manhattan, a T-2 tanker built in the same way, cracked so badly her crew ran away in fear. Between 1943 and 1944, more than 2,500 Liberty ships had big structure problems, cracks in the sides, decks, breaking, and full splits. At least 19 of them broke right in half, and 3 were lost at sea so fast they could not even send a help call. These were not battle losses, they were ships breaking themselves. America had risked everything on the Liberty ship plan. After the Pearl Harbor attack pulled the United States into full war, the country needed cargo ships, fast hundreds of them. Old shipbuilding took 8 months for one ship, and that was too slow. Henry Kaiser, a builder who had never made ships before, made a bold promise to make cargo ships like cars built on fast assembly lines in weeks, not months. His yards in Richmond, California used new ways welding instead of rivets and ready-made parts instead of slow building piece by piece. The setup came from car factories in Detroit. By the end of 1942, his shipyards were launching Liberty ships in about 42 days. News films called it an industrial miracle, showing happy workers like Rosie the Riveters, though now they were really welders turning steel into ships at amazing speed. The ship SS Robert E. Perry even set a record in November 1942, built in only 4 days and 15 hours from start to launch. Americans cheered because the Allied cargo ships that had been destroyed by German U-boat wolf packs now had strong new support coming fast into the Atlantic Ocean. But soon the ships began breaking apart not from torpedo hits or bad weather, but suddenly and completely even when the sea was calm. Ship designers were totally confused. The welds looked firm. The steel matched all the right standards. The plans came from trusted British designs. Yet the Liberty ships were cracking apart like fragile teacups. The cracks usually began around sharp corners, hatch openings, gun mounts, or in the square shape of the hull. Once a crack began, it spread through the welded steel plates very fast, sometimes running the full length of a ship in only seconds. The Maritime Commission started quick emergency studies. Metal experts looked at the broken steel under microscopes. Engineers checked all the pressure math. Navy inspectors crawled through every hole with their measuring tools. Everyone looked for the cause: bad steel, bad welds, poor design, or weak quality control. But the ships kept splitting while groups argued. Sailors became scared of their own ships, knowing the floor under their boots could rip open anytime in the cold Atlantic water. The great success of fast shipbuilding had turned into a sea disaster, and nobody could explain why ships built in record time were failing in record numbers. The answer finally came from a place nobody expected: a welder working on the factory line who was not supposed to question the engineers. Her name was Bessie Hamill, and she worked nights at Kaiser's Richmond Shipyard Number 3. She was one of thousands of women who took shipyard jobs after the men left to fight in the war overseas. She had been welding ship parts for 8 months, long enough to notice something the engineers missed. Every night she saw her team weld big steel plates in a way that made no sense. Hamill saw welders starting at the plate edges and welding toward the middle, or beginning at one end of a long line and going straight to the other. When each weld cooled, the metal tightened, pulled, and bent the plates. She could see the stress grow and watch the steel twist under her torch. When welders finished one part and started the next, they were locking that stress into the ship forever. It was like tightening the middle bolts on a car wheel before the outer ones, which always causes imbalance and failure. Her boss ignored her warning. She was only a welder, she was not an engineer. The welding order came from the engineering office, from men with college degrees and naval design training. But Hamill kept trying. Anyway, In November 1943, she asked for a meeting with his shipyard bosses even though it broke the rules and could have gotten her fired. She brought sample plates she had welded during her own time using different welding orders. Some of them showed bad bending and clear stress marks. Others that she welded starting from the center and working outward stayed flat and smooth with almost no bending. The bosses doubted her at first, but were also curious. One agreed to come and watch her team during her shift. What he saw proved she was right. The welders were basically hurting the steel, forcing it to hold strong stress for its whole working life. Every time a weld cooled, it made leftover tension inside the metal. The building order caused these hidden stresses to collect in certain places like the corners of openings and other tight spots. When those ships hit the icy North Atlantic water, the steel turned brittle and weak. The locked-in stress mixed with the brittle steel made the perfect setup for sudden cracks. Hamill's idea was simple but smart. Start welding from the middle of each part and move outward so the stress spreads toward the edges instead of gathering in the middle. Switch welding spots often to stop too much heat in one place. Never finish a weld in one long line. Instead, follow a balanced plan that spreads the stress evenly as the metal cools. These were not fancy science ideas. They were just smart lessons from someone who worked with the metal every night, who could feel it move under her torch and see what it did. By December 1943, her notes reached Henry Kaiser himself. He had a hard choice to make. The Liberty Ship program was already under pressure from Congress because of all the cracks. Saying the problem came from the welding order, not the steel or weld quality, meant admitting every ship so far had the same built-in weakness. It meant stopping production for a while to retrain thousands of welders. It meant changing how every part of the ship was made. But it could also fix the breaking problem that was hurting America's warshipping system. Kaiser, to his credit, did not delay. He ordered quick tests of Hamill's plan, pulling a whole ship section from the line to rebuild it her way. The metal experts and engineers who had spent months studying broken ships were now learning from a night shift welder who had never been to college. The test results were shocking and exciting at the same time. When Kaiser's metal team studied ship parts built the old way and Hamill's new way, the change was huge. Stress meters showed the old welds carried inside pressure over 30,000 pounds per square inch gathered at key points. Hamill's new weld pattern spread that pressure wider with top readings around 12,000 psi. The steel itself was exactly the same. The welds were chemically the same as before. Only the order of the work had changed, yet the ship's strength improved by amounts the engineers first refused to believe. The science behind the breaking finally became clear. Steel is not still or unchanging. It is a crystal-like material that reacts to heat and cold. When welders move a torch along a line, they make a super hot zone that can reach over 2,500 degrees Fahrenheit. The metal grows and expands in that heat. When it cools, it shrinks, but the colder steel around it keeps it from shrinking fully. This traps tight pulling stress inside the metal forever, unless the welding order lets that stress spread out slowly. The Liberty ships were being damaged by what metal experts call brittle fracture spreading. The kind of steel used in their hulls, called carbon ship steel, worked fine in warm water, but changed when it hit the freezing North Atlantic. Below about 40 degrees Fahrenheit, the steel lost its ability to bend. Normally, metal handles stress by bending a little instead of breaking. But cold steel loses that bend. It becomes stiff and fragile like glass instead of tough, like the steel the welders used back in California's mild weather. When this stiff steel met trapid stress at a sharp spot like the square edge of a cargo hatch, the laws of physics took over fast. A tiny crack started. In softer steel, that small crack would stop because the metal can stretch. But in cold, stiff steel under pressure, the crack ran wild. The trapped energy inside those stresses gave the crack power to spread. Sharp corners made that stress even worse, sometimes tripling it. The crack sped up fast, sometimes even faster than the sound moving through the metal racing across the hull, before any walls or beams could stop it. The SS Skenktedy's break now made perfect sense. She was built in early winter, welded in a way that locked in stress. Her hull carried millions of pounds of tight tension. When the Portland air dropped to 28 degrees, the steel turned brittle. The stress at one hatch corner started a crack. That crack found a straight path through the long welded deck plates. There were no rivets to slow it, no brakes to release the stress. The crack tore through the ship in seconds, letting out huge stored energy all at once in a total failure. Older riveted ships did not have this problem, and that difference helped explain why welding looked accursed. Riveted construction is naturally discontinuous. Each riveted plate is a separate piece of metal. Cracks that begin in one plate hit a riveted seam and then stop. The overlapping plates and the metal fasteners act like built-in crack stoppers. Welded ships are continuous structures. A crack in one plate can move freely through hundreds of feet of welded seams without stopping. The same efficiency that made welded ships faster and cheaper to build also made them weaker against the kinds of failures riveted ships never faced. The Liberty ship's squared-off shape made the trouble even worse. British ship designers had chosen those hard corners to make cargo loading easier. No one thought about how sharp inside corners make stress build up fast and multiply the load by huge amounts. Every ocean wave that bent the hull sent quick stress shocks through those corners. When that pressure mixed with locked-in welding stress and brittle steel, those corners became cracked starting points, waiting for the right cold moment to break apart completely. Henry Kaiser knew what the new test results meant for his factories and for the war itself. In January 1944, he made a bold choice that could either prove his industrial revolution right or expose him as a greedy builder who had sent thousands of sailors to sea in bad ships. He ordered all Liberty shipbuilding at Richmond Yard to stop and moved everything toward a totally new kind of ship called the Victory ship. This was not just a small fix. It was a deep redesign based fully on Bessie Hamill's welding lessons and on the painful truths found in the broken hulls across both oceans. The risk was huge. Liberty ships were still badly needed. German U-boats had sunk more than 2,000 Allied cargo ships since 1939. The coming invasion of Europe, still months away, would need the biggest sea supply effort ever in human history. Every single ship mattered. Yet Kaiser was taking a huge bet that he could use Hamill's new welding pattern, change the hull shape to remove stress points, improve the steel quality, and still keep up his amazing building speed. His rivals thought he had gone crazy. Lawmakers in Congress were ready to attack him hard if production slowed. Kaiser's engineers began studying from the breakpoints backward. Every square corner in the Liberty ship design was replaced with smooth, rounded curves. The hatch openings that had started so many cracks were redesigned with wide, gentle shapes that spread out the stress instead of focusing it into breaks. The deck and hull plate thicknesses were recalculated not to add more raw strength, but to make sure stress spread evenly with the new welding order. The structural frames were moved and realigned to match the new natural flow of stress. The new ship frames were now placed to line up with natural stress relief points instead of pushing against the welding pattern. The steel itself was also changed. Kaiser's metal experts created a new alloy type that stayed strong even in very cold water. They lowered the carbon level a little and raised the manganese level. They also added small amounts of nickel, which was rare and costly because it was used mostly for armor steel, but they proved that just 0.25% nickel made the steel much less likely to crack in cold weather. The Maritime Commission first complained about the extra cost until Kaiser showed math, proving that saving even one ship from breaking apart would cover the cost of better steel for 50 other ships. In March 1944, the new steel plan was finally approved. Then began the huge task of training the workers all over again. By early 1944, Richmond shipyards had over 90,000 workers. Thousands of them were welders who had learned their skill in short crash courses, just long enough to run straight weld lines at high speed. Now they needed to understand sequence order, heat control, and how to release stress. Kaiser built welding schools right inside the shipyards and pulled skilled welders like Bessie Hamill off the main line to teach. Every welder got a numbered card for each hull section, showing exactly where to start and where to go next, never changing the order. The factory setup grew much larger. Instead of welding giant hulls on open ways where it was hard to control the order, Kaiser's team divided the new Victory ships into smaller parts made in special workshops. A bow section could hold 50 smaller, pre-made pieces, each welded carefully under perfect conditions and heated afterward to remove leftover stress before being joined to the hull. This new modular system meant every welder could start from the middle of each small part and move outward exactly like Hamill had shown, without the trouble of working on a full-size ship. Critics got loud when the first Victory ship keel was built in February 1944. It took 18 days, slower than the fastest Liberty ships. Kaiser's shipyards no longer broke records but still worked fast. The second Victory ship took 16 days. Critics called it proof that quality and speed could never work together. Kaiser ignored them completely. He watched the crack inspection results instead of timing charts. The first two Victory ships showed no stress cracks at all. After they were built, not fewer cracks, but zero. By April 1944, Richmond Yard, two had turned into a perfect dance of steel, fire, and teamwork that would have looked impossible only 2 years before. The yard did not look like a regular shipyard anymore. It looked like a huge factory with many work areas feeding into one big place where ships took shape fast enough to amaze everyone. Kaiser had borrowed Henry Ford's moving assembly line idea, but instead of the ship moving, the work teams moved between fixed building spots at set times. The work started inside big covered sheds where welders worked on hull parts no bigger than 30 feet in any direction. Each part had its own instruction card showing the order of welds. A bottom plate might need 47 welds that were numbered and color marked. Welders always began at spot 1, which was the exact middle of the part, and then worked outward in a spiral shape. Supervisors walked the area holding checklists to make sure no one jumped ahead. After every 10 welds, the part was heated inside a special oven at 2,100 degrees and cooled down slowly. This heating step let the steel's crystal structure relax and release leftover stress before it could build up too much. The steel itself came already cut and shaped from big rolling mills that had changed their machines just for Victory ship work. Unlike Liberty ships where workers had to cut and shape plates by hand at the yard, Victory ship parts arrived already ready to fit. Curved front pieces came shaped to exact size. Deck plates already had holes drilled for quick setup. Frame parts came partly welded and ready to use. Doing this prep work inside safe factory buildings made sure every piece fit right and matched every time. The main ship assembly followed a new order compared to Liberty ships. Instead of starting from the bottom and going up, Victory ships were built from big sections that came together almost at once. The engine area, cargo spaces, front and back were all made at the same time, then lifted with giant cranes and placed together in one careful move. On May 12, 1944, Yard 2 did its biggest build ever. 17 huge sections that made up 85% of a full ship were lifted and fitted in only 11 hours. Welders joined those parts using the same center outward order, but now they were connecting stress-free pieces instead of making new stressed ones. The 5-day build goal became real because every second of work was planned and improved again and again. Night shifts got materials ready for day shifts, while special teams did nothing but check alignment and weld quality so they could catch mistakes before they spread. Mobile cranes followed planned routes, bringing parts to welding spots right on time within 5-minute windows. Welders worked in turns, spending 30 minutes on the torch, then taking 10 minutes rest to keep steady quality without the tired mistakes that ruin long welding work. Kaiser used what he called the critical path method, which meant watching closely which jobs caused slowdowns and which ones could move ahead together. If framework finished early, but pipe fitting was slow, he quickly moved workers to balance everything across each build stage. Every small delay and every change from plan got written down and studied. Morning meetings looked at the last day's work, finding answers before tiny issues turned into big slowdowns. The record came on June 27, 1944, when the SS Benjamin Warner Victory ship, hull number 23, was built from start to sea testing in just 5 days and 11 hours. It wasn't a quick test ship, but a fully ready, fighting cargo ship with weapons-full electric systems, a working engine room, and every rivet, or better said, every weld made by the new stress relief rules. She had no hull cracks at all. Her checks after building showed stress levels well inside safe limits. When the Warner sailed for her first test trip, she ran perfectly in weather that would have broken the early Liberty ships. The 5-day Victory ship was not only about fast building, it showed a whole new way to make big machines when smart design worked together with real hands-on skill. Bessie Hamill's small idea had spread into a full change in how ships were built. The Victory ships from Kaiser's new system were totally different from the Liberty ships before them. Even though to most people they looked like the same cargo ships doing the same work, the change started inside the steel itself and reached through every part of design and making. Where Liberty ships had been quick emergency fixes, Victory ships were careful plans that solved every danger written in the lives of sailors who had gone down with broken ships in the icy Atlantic. The better steel recipe made a big difference. The new alloy, called killed steel because aluminum was mixed in during making to remove oxygen, showed much stronger toughness in cold water. Lab tests proved the temperature change point. The temperature point where steel changes from bendable to brittle had dropped from about 40 degrees Fahrenheit in Liberty ship steel to nearly 5 degrees. This 35-degree improvement meant Victory ships stayed flexible in cold seas that made Liberty ship hulls weak like glass. The extra cost was only 8% per ton, but the performance gain was priceless. Every small detail in their structure showed the new understanding of stress and crack spreading. The rounded hatch corners that looked like a small design change actually lowered local stress by more than 60%. Engineering notes showed that the sharp 90-degree corners in Liberty ships created stress levels 3.5 to 4 times higher than the normal hull stress. The Victory ship's smooth curves kept that number below 1.8. In simple words, a wave strong enough to start a crack in a Liberty ship only made a Victory ship bend safely inside normal limits. The hull plates themselves were built with crack stopper features already inside the design. Instead of long, endless welds running hundreds of feet, Victory ships used riveted seams placed at smart points. These mixed joints created breaks where a running crack would hit a rivet line and lose energy before it could eat the whole hull. The design expected that cracks might start, but it made sure they could not spread far. It was careful, safe building that planned for failure instead of pretending failure would never happen. The steel frames were doubled at hard stress points, giving backup support paths. If one frame cracked, another nearby frame could hold the load until the ship reached port for repair. Liberty ships had no such backup, so one broken frame could cause the rest to fail fast as stress jumped from one to another. Victory ships could take hits that would sink a Liberty ship and still keep moving slowly back to port with damaged but strong enough parts. The welding steps based on Hamill's discovery were written into big instruction books that guided every single weld on every ship. The rulebooks filled hundreds of pages telling not only the order, but also how to control heat between welds. Welders learned to check the inner pass temperature, which means the heat in the steel between each pass. If the steel went over 400 degrees, work stopped until it cooled down naturally. This prevented the buildup of extra heat that caused big warping problems in Liberty shipbuilding, where welders often worked nonstop on long seams, overheating the steel until it bent and filled with stress. Quality checking became almost like an obsession. Every finished weld was tested with magnetic powder and magnets that made tiny cracks easy to see. Sound wave testing checked inside the weld to make sure it was solid all the way through with no empty spots. X-ray checking was used on the most important parts, making permanent pictures that proved the welds were good. Ships were not launched until inspectors said every weld was perfect. At first, about 15% of welds failed the test on the first Victory ships, but workers learned fast. By the middle of 1944, the failure rate dropped below 3%, which showed how well the training and nuclear rules worked. The proof came when the ships went to war. Between June 1944 and the end of the war in August 1945, 531 Victory ships were launched, and not one broke apart or failed completely. Only a few got small cracks that inspectors found before they grew. Those cracks were fixed with the same stress relief welding steps, and the ships went right back to duty. The difference between Victory ships and Liberty ships was total and shocking. The math of saved lives and finished missions proved it clearly in both oceans during 1944 and 1945. The SS Wanda Fuka, a Victory ship, hit a mine near Okinawa in April 1945. The blast made a 20-foot hole in her side under the water, but instead of splitting like Liberty ships, she stayed together because the crack stopped at the first riveted crack. Arrest or seam. She reached port using her own power, got fixed in 6 days, and went back to sea. A Liberty ship with the same kind of hit, the SS Richard Hovey, was not so lucky. It cracked for more than 90 feet, broke in half, and sank in 14 minutes, killing 37 sailors. The Pacific War supply line could not have worked without the strong and reliable Victory ships. By June 1944, American forces were pushing across the Central Pacific toward the Philippines and later Japan. Every island they took needed millions of tons of supplies, carried over thousands of miles of ocean. Liberty ships could make those trips, but their weak structure meant they had to carry less cargo in rough water, travel slower to reduce hull stress, and always risk breaking apart far from help. Victory ships could carry full loads at their top speed of 15 knots, which was 3 knots faster than Liberty ships, and they could do it through storm-filled seas without fear that a cold night or rough waves would tear the ship in half. The numbers showed the truth. From D-Day in June 1944 to VJ Day in August 1945, Victory ships moved more than 18 million tons of cargo with zero losses from hull failure. They sailed in North Atlantic convoys, where the water often dropped below 35 degrees, cold enough to snap Liberty ships apart. They also went through the Arctic routes to Murmansk, bringing Lend-Lease cargo to the Soviet Union, where freezing seawater made Liberty ships dangerously weak. The SS Hobart Baker, a Victory ship, made 17 Murmansk runs without a single crack. The Liberty ship John Walker, doing the same route, cracked badly on her second trip and was removed from Arctic duty forever. Crew morale changed completely when sailors moved from Liberty ships to Victory ships. Stories collected after the war showed how stressful it had been working on ships that could break without warning. Many mariners said they were always tense, especially when it was cold. Sleeping was hard because every sound of the ship could mean it was breaking. Some asked to transfer or flat refused to sail on certain Liberty ships known for cracking. Victory ships gave sailors confidence again. Crews pushed them harder because they trusted the ships could handle it. That trust made missions faster and safer, with shorter stays in port and no fear of sailing in bad weather or turning fast under attack. The Battle of Leyte Gulf in October 1944 proved how strong Victory ships really were, even in the worst conditions that would have destroyed Liberty ships. 16 Victory ships supported the invasion fleet, carrying bombs, airplane fuel, and supplies through kamikaze attacks and typhoon winds. The SS Kyle Johnson took near bomb hits that bent her deck and cracked 3 frames, but she kept working, unloading supplies under fire for 4 days before pulling back for repairs. The extra frames and crack-stopping features kept small damage from turning into a total disaster. Liberty ships with the same kind of damage usually had to be abandoned because the cracks spread too fast to control. The money math was harsh but simple. Each Liberty ship cost about $2 million to build. Victory ships cost $2.6 million, 30% more. But a Liberty ship had a 4.6% chance of breaking apart completely during its service based on real failure rates through 1944. Those failures killed an average of 18 crew members per incident and ruined cargo worth 3 to 5 times what it cost to build the ship. Victory ships with 0 failures meant that the extra $600,000 was paid back in the first 6 months just by avoiding losses and lower insurance costs. By the end of the war, sailors had a grim saying that showed the difference. Liberty ships were built fast by the mile and cut off at the yard. Victory ships were built carefully by the inch and counted for years. Those careful inches, the attention to weld order, the strict quality control, and the crack-stopping design meant decades of service instead of praying every time the hull groaned in cold seas. Bessie Hamill went back to normal life in 1946 with no big celebration or awards except a letter of praise from her supervisor. She never got a medal, never spoke to Congress, and never saw her name in the technical papers that later described the welding revolution she started. The engineering world took her ideas, put them in math and academic words, and published them as if the discoveries came from a lab instead of a night shift welder's hands-on work. For decades, the welding textbooks taught stress relief welding without mentioning the woman who first saw why it was needed while watching hull plates bend under her torch. Still, her work affects modern engineering far beyond ships. Every welded building today, from tall skyscrapers to pipelines to pressure tanks, uses welding steps that came straight from Richmond Shipyard in 1944. The American Welding Society's welding code first came out in 1947 and made center outward welding and stress relief rules mandatory. Pipeline work in Alaska in the 1970s used welding methods that directly followed Victory ship rules to stop cold weather cracks in Arctic conditions. The Trans-Alaska Pipeline, 800 miles of welded steel carrying hot oil through sub-zero temperatures, exists because engineers learned the lessons Hamill taught. Modern bridge building followed the same ideas. The deadly collapse of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, included leftover welding stress as one reason. The investigation showed welds done without proper order had trapped stress in key parts of the bridge. After the disaster, building rules were changed to require the welding order and inspections that Victory ships had started. Every welded bridge built after that used these rules. The Golden Gate Bridge seismic upgrade in the 1990s, which added thousands of tons of welded steel, used computer-planned welding orders made to lower residual stress. These were high-tech versions of what Hamill showed with hand-welded plates back in 1943. The offshore oil business learned the lesson many times. The Alexander Kielland platform accident in Norway in 1980, where 123 workers died when the platform toppled, was partly because fatigue cracks spread from welds done in the wrong order. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe that had trapped stress. Each disaster made investigators check welding methods, and each time, they rediscovered what Victory shipbuilding had proved 40 years earlier. Today's offshore rules require stress relief heating for all critical welds, which is directly from the ovens Kaiser used in Richmond's prefabrication sheds. Nuclear reactors, with steel shells holding extreme heat and pressure, are the most important example of stress relief welding. These huge steel containers cannot allow even a tiny crack. Weld sequences for reactor vessels are planned with the computers to check heat and stress before the first weld. Then the whole vessel is heated in big ovens just like Victory ship sections were, getting rid of trapped stress that could start a failure. Engineers in the 1950s studied Victory shipbuilding as the main guide for these rules. Hamill's observation changed the way engineers think about how things are built. Before Victory ships, designing and building were separate jobs. Engineers designed structures, fabricators built them, and the two groups hardly ever talked about how building methods affected the strength of structures. Victory ships showed that the order of building was just as important as the materials used or the design itself. Today, engineering schools teach manufacturing processes as a key part of design classes. Students learn that a perfect design done with a bad building order gives worse results than a simpler design done with correct steps. The 5-day building time, though amazing, was never the real success. Kaiser's shipyards could have kept up Liberty ship speeds forever, making ships that looked fine until they broke. The real miracle was slowing down enough to do it correctly. Having the courage to stop production and redesign methods based on a welder's insight that went against the usual rules. That willingness to listen to workers on the floor and to admit that engineering theory had missed something important, and then redesign systems based on what actually happened instead of defending assumptions. This was the real change. Every modern manufacturing method, from Six Sigma to lean production to total quality management, uses this idea. The worker watching the process often sees things the engineer calculating at a desk cannot. Bessie Hamill died in 1987 in Sacramento, and her obituary only mentioned that she worked in wartime shipyards. But every welded structure standing today, every pipeline crossing frozen land, every pressure vessel holding dangerous forces, every bridge over rivers, all carry her legacy in their ordered welds and stress-relieved joints. Silent proof of the welder who asked why ships were breaking and refused to accept that that's just how it's done as an